Okay, hello. Um, I'm Sean Eagan, and in thinking about this presentation, I'm trying to think back of when I learned most of what I know about streams, and it was my 7 years with the Pacific Southwest Research Station, where we were instrumenting 8 small streams in the Sierra Nevada and collecting nutrient samples and sediment and turbidity and temperature, and visiting streams twice a year for 6 or 7 years, not twice a year, twice a month for 6 or 7 years taught me a lot. And now I've been up here in Alaska in the Tlingit-Ani territory here in Juneau for 7 years, and some of those lessons transfer over and some of them don't. But I'm going to first talk to you about stream temperature, and then I'm going to move on to talking about erosion. Okay, so stream temperature is affected a couple weeks of the year by all of these things. Anytime you get a big rainfall event, an inch or two, you're going to start getting some overland flow, and your stream temperature is going to come close to the temperature of the rain. But that's not just showers, that's a couple days of rain all in a row. And snow melt, especially in the spring, if it's really hot, you can melt enough snow that you start seeing the stream temperature go pretty close to zero, that same temperature of the melted snow. But a lot of the year, the snow is either not melting or melting extremely slowly, and it's just going into the groundwater. And on those days, it's not affecting stream temperature. If you've worked in Southeast Alaska, you know that most of our streams have a really tight canopy of tall trees. They don't get much direct sunlight. But sunlight, especially in July, can affect them. Some of our streams are fed by high alpine bogs and meadows. And so if you've got sun beating down on the grass, the wetland up there, you can heat that whole thing up, and that warm water can move into the stream, making the stream warmer. And finally, you might think that air temperature affects streams, and it does. But there's not actually a lot of heat being transferred from the air into the stream. But over time, if you have a bunch of hot days, it affects a little bit. However, there's one thing that is way more important than those first four. And that is shallow groundwater. And I think a lot of people slightly intimidated by groundwater. We've never seen it. You've heard about this ancient groundwater that's been in the ground for a year or a decade or a millennia. But this is a different sort of groundwater. This is the sort of groundwater where it rains hard for 3 days. The soils of the southeast or other mountainous ranges soak up moisture in their first, say, 4 feet. Generally, our soils are not that deep. So 4 or 6 feet down, the water would hit bedrock. It wouldn't really be able to go through that, and it would move sideways to the closest local stream. So it's just dripping down off the trees, hitting the soil, going into the soil, depending, maybe it's in that soil for 2 days, maybe 2 weeks, maybe 2 months, but it's not a tremendous amount of long time. And it's coming to the same temperature of that soil. And then 365 days a year, it is feeding into the bottom of these small streams. And it's really what's making the streams good habitat for salmon, because that shallow groundwater is consistent, and it's a temperature that they like, somewhere between 32 and 45 Fahrenheit. So shallow groundwater is super important. So really none of us has ever seen groundwater exactly. So my closest approximation is this is my house in Juneau, and there's some fill to make it level built on bedrock. And so I've got a lawn that sits on about 2 to 3 feet of fill. And that lawn and the soil underneath soaks up groundwater, and then it percolates through those first 3 feet till it hits a layer that doesn't let the water go through as much. And it hits a layer of high hydraulic conductivity. So if you see those gravels right there, that is a gravel layer that's down there. It hits that, moves sideways, and washes out onto my driveway, creating an ice slick. So whether it's warm or cold, winter or summer, If it's rained within the last week, that little bit of gravel seeps out water. So the groundwater going into streams, don't think of it as a single source where you could find it and tap it. Think of your stream as 2 miles long, and it's just dripping in, seeping in all along those 2 miles, little bit by little bit, not a single source. So stream temperature varies by where you measure it. If you've got a deep pool, those can stay warmer in the winter. So they might have ice on top, but underneath there's good rearing habitat for juvenile salmon. They may stay cooler in the summer. If you've got a pool that's 4 feet deep, it's intercepting a lot of layers of groundwater. So it's got a lot more groundwater influence than if you've got a riffle that's only 3 inches deep. Another important thing to think about temperature is that adult fish and juveniles, if they don't like the temperature, they'll tend to swim to some other spot in the stream where they do like the temperature. But if you're in the egg stage, the salmon egg stage, you can't move. So the most important place to get your temperatures right is in the spawning gravels. If the spawning gravels are high quality gravels with a lot of water interchange, they're probably the same temperature as the water above. If they're more filled with fines, they could be different temperature. But if you're really worried about your salmon, try to measure the temperature in the spawning gravels, because that's where it's most important. If you've got riparian trees, obviously they can keep the stream a little bit cooler in the summertime, and they actually keep it a little bit warmer in the winter. So why do we care about stream temperatures? As I just said, the most important thing is we have to make sure our salmon redds do not freeze. If you've got sufficient water in the winter, you can get a little bit of ice on the surface and you can still have flow underneath. And we actually in Juneau showed in one spot where we actually froze the top inch of the gravel layer, and those eggs were killed. But some of the salmon had laid their eggs down 3 or 4 inches deeper, and there was still water moving through that. So ideally you want some flowing water, and at least you need the water flowing through the spawning gravels. If your streams are too cold or too warm, you can delay or speed up when the eggs hatch and release the fry. You want your fry to release when the food source, the macroinvertebrates, are available for them to eat, or in the case of pink or fry going straight to the ocean, they want to arrive at the right time. So for instance, if you had a stream that was 1 to 2 degrees for a long, long time, all winter long, and all of a sudden it's 4 degrees, your eggs are going to mature that much faster. They're going to hatch out in February, maybe March 1st. There may not be the correct food sources for the fry. So it's important to keep your temperatures what the fish are used to. I call it an evolving worry, but I think in 2015 and 16, we got some streams in Sitka that got so hot that they killed salmon because climate change is making us hotter. And if I have my dates right, the same thing happened in Anchorage and the Kenai Peninsula around 2019. So although California has been dealing with too hot streams for 35 years, up in Alaska, it's in the last 5 years, but we're going to have to keep looking at this. And finally, warmer water increases algae. The algae die, decompose, and as they decompose, they use up oxygen, and so you have lower oxygen streams, which once again, you can get your oxygen levels too low for your salmon. So you might think, okay, I want to make my stream, I want to pay attention to my stream and see if it's right for Pacific salmon. And you can go to a textbook or a paper, and they'll give you some numbers. These numbers are way oversimplified. When they say salmon don't want to migrate through 15 degrees Celsius water, that means they don't want to pass through a chunk of water that's that hot. But if you ask them to swim up a stream that's 13 degrees Celsius for 3 days, that's not going to work either. So these guidelines are oversimplified, and they're not the same for all species. So for each species of salmon, you would have a different temperature you would like the eggs to be at, a different temperature for juveniles, different temperature for adult spawning. And going beyond that, when I arrived in Alaska about 7 years ago, I got these words confused: stock, distinct population segment, ecological significant unit. Each of those words relates to a different federal act, but they're all saying the same thing. They're saying salmon in a local area interbreed, and they have similar temperature requirements. So in the upper right, I have a picture of a coho salmon, the Central California coast coho. So it's on the endangered species list. It's a separate subspecies. You're like, okay, that's different because it's been labeled a separate subspecies. Those coho have, they haven't gotten lucky with the coho from Juneau in the last 100 generations. So because they're not interbreeding at all with our coho, they're used to a different set of stream temperatures, and they're genetically different than our salmon in Juneau. Now our salmon, our coho in Juneau might be pretty similar to the ones in Petersburg and Haines, but they're not similar to the ones in the Susitna or the Yukon. Those fish are going to be used to colder weather. They're going to have their timing such that they can deal with the river freezing up earlier, less open water. So although we haven't differentiated different populations within Alaska, they are different. So know your local salmon, know the requirements of that species in the area you're working. And then you can know whether your stream has temperatures that are appropriate. So the stream temperature takeaways are: one, groundwater is super important. It affects stream temperature 365 days a year. Without groundwater, very few streams would be good for salmon habitat. Stream temperature varies by location. The most important is the temperature in the spawning gravel. Both streams that are too cold and too warm can cause problems with timing of egg release. And finally, understand your local fish. Don't go to a publication or a textbook and come up with one set of answers. Know your local fish. So I'm moving on to erosion. And erosion is not all bad. It's a natural process. Too much erosion can create some problems. So this is a classic theory of stream hydraulics. You've got this stream meandering down a valley. If you throw a stick in and you look at the surface currents, you realize that they hit the outer bend of the river and they cause a little bit of erosion right there. A secondary thing is coming up. In addition to what you're seeing on the surface, there's a circular flow of currents that are generally working like a shave ice and just pulling off a couple particles off the outside of that bend and bringing them downstream to the next point bar. And so there's lots of books that show you this, but there's some really important caveats to make this system work. And one is that the banks are vegetated with grass or shrubs. Roots don't go too deep. The next is you have consistent bank material. In this picture, it looks like it's gravels, but you know, it's gravel, sandy loam, silts maybe, stuff that's erodible in small chunks. The third thing is your stream needs to be at equilibrium. It's not incising down into the valley. It's not grading up. Maybe it's been flowing down this valley for 5 million years. It's at a 0.5% gradient or maybe a 0.25% gradient. So the stream has to be in equilibrium. And finally, you need a nice wide valley, maybe a 1/4 mile or a 1/2 mile wide, where these meander bends can go out and come back in, and they slowly move. And it's an organized system. Now, I've looked all around Southeast Alaska, and I simply cannot find this.
2-minute warning there, Sean. Thank you.
Okay. So Southeast Alaska streams mostly ignore those channel hydraulics. Our mountains have been accreted onto the continent in the last couple million years, same as the mountains on the Kenai Peninsula, Kodiak. These young mountain ranges are extremely steep, and they simply function in a different way. So this is a typical stream in Southeast Alaska, Gold Creek here in Juneau. As you can see, it's eroding the banks. There's the soil's pretty shallow. There's some bedrock in the front of that picture. And there is some bank erosion. This stream is somewhere between 2 and 5%. It's too steep to ever meander. It's never going to do that nice meander pattern. And if you look carefully at this, these rocks aren't very rounded. They're kind of angular. And with a name like Gold Creek, yes, there was mining here. So you might say this isn't a good example, but it's a great example because any place we're building roads probably had mining or logging in the past. And you should look back and understand the history of your stream and how those people may have altered it, and you'll have a better idea of how to keep your culvert or bridge intact. So I don't want to imply that all of our streams are super steep. This is Montana Creek. There was some bank erosion on the far side, on the left side, and it caused this tree with its root wad intact to tip over. And right now, that tree is creating the erosion because the stream is going behind the root wad at the far edge of the picture, and it's coming in front of it close to us. So it's widening the stream out to get around that log. So yes, the tree trunk is creating erosion, but it's also doing a great job of sorting gravels. We've got finer gravels downstream. It's doing a great job of creating pools. So it's creating erosion, and it's also creating excellent fish habitat. So this is a TNC illustration by Erica Sloniker. Once again, those nice meander bends create the deep holes, the riffles, the spawning gravels in an older system. In the younger systems we have here in the Southeast, logs and boulders create the same diversity of habitat. Salmon, just like land animals, like diversity of habitat. If you give them enough diversity, they can find pools for holding, they can find gravels. This woody debris brings in macroinvertebrates. So wood is very important in Southeast Alaska streams and any mountainous range. Most of you guys know that this part of Alaska, the Panhandle, is a rainforest. 150 inches of rain down in Ketchikan, 70 inches here in Juneau, 45 inches up in Haines. All that rain doesn't mean erosion. All that rain gives you a ton of vegetation, and vegetation undisturbed can hold banks intact that you would think would be eroding left, right, and center. So vegetation is very good at stopping or eliminating most erosion. The problem comes in when we remove the vegetation and allow the bare soil to be hit with the heavy rains. So in this case, this road is just dirt, and you can see it. There's a lot of erosion going down it. You may not know which stream it's going to end up in, but it will end up in a stream. So when vegetation is removed, you have to think about if the money was available, a little bit of gravel on this road might have helped the situation. So I don't want to leave you with the conclusion that only humans create erosion, because that's not true. Especially in desert environments, you often have a steep stream coming out of a side canyon, and it's held in place, and then when it hits the valley bottom, it forms an alluvial fan. So it's bringing all this sediment down during a big rainstorm, and then it's fanning out to the left and to the right. They can be 400 yards wide, they can be a half mile wide, these fans, and each rainstorm more stuff comes down. So in this case, an alluvial fan is encroaching on the Eklutna River up near Anchorage. This is not the outside of a bend, and the Eklutna River is, it tends to run turbid, I don't know, half the days of the year. And it's because it's just constantly removing material from the toe of that alluvial slope. And it's the process of the fan trying to get bigger is continuous, And the process of the river trying to take back territory is also continuous. Another completely natural source of sediment is we are getting more of these really big rainstorms in Southeast Alaska where you get 8 to 10 inches of rain in 3 days. And we tend to have landslides. So the landslide brings a huge amount of material down and dumps it in a stream or in a river valley bottom. And then that river or stream is going to take the next couple of years just chewing away at that huge piece of mud and trying to get it out of the way so it can have its channel back. So the message is there are some things that humans do that increase erosion, and there's also some natural causes. So lastly, this is Pelican Creek. And there's a lot of processes going on at once. If you look in the bottom right, you've got bedrock. That's not creating any erosion, and it's going to hold the channel in place. If you look about in the middle, there's some rock fall that created that cascade. Not much erosion through a rock fall zone. If you look in the left corner, we've got some sorted gravel. This is sort of different than a point bar, but the stream hydraulics are still creating pockets of gravel and runs and riffles that are good for spawning and salmon habitat. If you look straight to the middle, this is a bend and the creek is going left. There's some tipped over trees that might have been caused by bank erosion, might not have. There's so much bedrock that it's hard for the bank to erode. But there's a little bit of a meander process going on. And finally, you've got this big Douglas fir tree on the left. And sooner or later, that's going to fall across the stream. It's going to create erosion, and it's also going to create great fish habitat. So don't think of a single process being one thing that controls your stream. It's a balance of these different processes all going on at once. So for the erosion takeaways, in these mountainous terrains of young mountains, woody debris, especially down trees with their root balls intact, they create erosion, and they also create fish habitat. Removing vegetation and exposing soil to hard rain causes erosion. Alluvial fans and landslides are natural causes of erosion. We're not going to stop either one. And in most streams, you're working on several processes that are happening at once. So think that through. And I want to thank you all for listening. And I don't know if I said it at the start, I'm on Tlingit Ani land, and I want to thank them for stewarding it so well for many, many, many generations. And actually, I want to thank the Forest Service, because I realized that most of what I learned about streams was my 7 years of field work, going out to those 8 same streams again and again and again. So thanks, Forest Service, for letting me spend so much time in the streams.